Okay, good morning everybody. My name is Mike Artenstone. I'm a lifelong electromechanical engineer, working in the construction plant industry, and recently I've started a new role as a mentor for our apprentices. So I thought it was very important to do this course to learn skills to improve my delivery and training skills. Could you please introduce yourselves and let me know a little about you, about who you are?
My name is Mia Stevenson, and I'm a training coordinator at Compass.
Sorry, what was your name again?
Mia.
Mia?
Yes. I'm Laura Smith, I'm also a training coordinator.
My name is James. I also work here at Compass, believe it or not, as an occupational health technician / health and safety man.
Good morning, James.
And I'm Sue Clifton, so I'm a functional skills tutor and also a tutor for education and training certificate.
Good morning, Sue. I've been informed that there's no special learning requirements today, and there are no planned fire drills. So if there is a fire alarm, just use the normal company policy for leaving the building at the nearest exit and assembling at the assembly point. A few ground rules before we start. If anyone feels unwell, please let us know so we can attend to that. If you need to leave the room, please just do so. Also, the golden rules, phones on silent, please, if possible. Are you all comfortable?
We're all very comfortable, thank you.
My presentation this morning is an introduction to electromagnetic induction. Do any of you have any prior knowledge of this subject?
Not much.
No, not
I
really.
did physics at A level, and that's about as much as.
So you may have come across some parts of this.
Well in the past, aye.
Okay, well I hope you're going to enjoy my presentation. So I'll get started. Electromagnetic induction. What is it? This is my agenda for today's, stand over this side. Introduction, who discovered this? What is electromagnetic induction? Which everyday devices depend upon this principle? And how do these devices work? An electromagnetic induction experiment, and then we will discuss what we've learned today. Introduction. Electromagnetic induction, it's the name given to the effect that occurs between a coil of wire and a magnet. This was discovered almost 200 years ago, which is amazing. It laid the foundation for the invention of many more devices and machines that changed everything. This was discovered by a guy called Faraday in London, Michael Faraday. And I just want to paint a little bit of a picture of contemporary London 200 years ago. The technology that existed at the time. People were using candles to light rooms. More wealthier people had gas lighting. Transport in London, horse and cart, or cabriolet, carriage and cart. And the Thames at the time was a sewer that was a very vital transport link for a lot of people crossing the Thames, which they did on little ferry boats called wherries. So you can imagine London at that time, there was no technology whatsoever. The Industrial Revolution had started, so steam engines were becoming more and more popular. Factories were growing. The industries, steel making or iron making, all driven by steam engines with enormous shafts running through the buildings with belts and pulleys. That was the rate of the technology at the time. It was grim. to say the least. And this guy, Faraday, was 39, 40 years of age. He'd been interested all his life in technology, but he served an apprentice for a bookbinder for 7 years, but because he worked for a bookbinder, he had access to books, so he read a lot, and he learnt a lot. He read books about improving the mind, and this led to his interest in science, and ultimately to the discovery of electromagnetic induction. A British pioneer in the field of electromagnetism discovered the phenomenon of electromagnetic induction in the early 30s and published what became known as Faraday's law. His continued experiments and passion for this subject led to his recognition as the inventor of the electric motor, the electric generator and the transformer. Also, Nikola Tesla was involved with electromagnetism and motors, and eventually he was acknowledged in 1960 when the unit of magnetic flux density equivalent to 10,000 Gauss was given the name Tesla, and of course more recently Elon Musk's electric car brand was named after him. But Faraday was also a member. He joined the Royal Society, the Royal Institution of Great Britain, the Science Institute, which was founded in 1799, and he often went there listening to lectures, but also presenting lectures on his findings. This was the modern day email, I suppose, or Twitter. They had nothing. They could write a letter, but people with similar interests would meet at the Science Institution and discuss what they were working on and what they discovered, which inspired other people to change the way they were doing experiments and carrying out their own tests. So what is electromagnetic induction? Faraday discovered that if you passed a magnet through a coil of wire, it would induce a current in that wire. And Faraday's law states that the electromagnetic force, the EMF that's induced in the coil, is proportional, directly proportional to the rate of change, to the speed that the magnet is flowing through the coil. I just wanted to demonstrate this quickly. This is the type of meter that Faraday used, albeit a modern version. If I just get one of these magnets out. You can see that if you pass a magnet, the needle deflects. It's only slightly, because it's a very slight current, but it's detecting it. Let's try that. If you do it somewhat a little bit faster, it moves a little bit more. But that is what Faraday discovered, which is quite underwhelming, really. That is such a small amount of current that is being generated there. But if you make this bigger, more coils of wire, bigger magnets, then you get more current. And that's what he discovered. And it led to many other things. He later discovered that by passing a current from an early type of chemical batteries, they didn't have batteries then that we have nowadays. They were jars of liquids and metals that produced a current. But from such a battery, we found that when a coil of wire with a current in it was placed near a magnet, it would turn towards the magnet. And if it did this and switched the poles, then the wire switched the direction of the current in the poles. The wire would rotate. And this was the very first experiment leading to the electric motor. How many devices that we have today depend on electromagnetic induction? Do you think many?
Probably more than you think.
Pardon?
Probably more than you think. Can imagine quite a lot. But
Hundreds more than you think. Hundreds more. There's probably 3 or 4 in here. 5, 6, maybe even more. But electric motors, they run our lives. All these items on here derive from the phenomenon of electromagnetic induction. Thomas Edison went on to develop and invent the light bulb. Alexander Graham Bell, the telephone. Samuel Morse, telegraphy and Morse code. Logie Baird, the television. And Marconi, Giovanni Marconi, radio waves. All were not possible without the discoveries of Faraday. Another application of the Faraday discovery is the electrical transformer, an electromagnetic device that could by means of induction increase or decrease the input voltage in an adjacent wire. So let me show you a diagram of that to explain it better. Here on this top picture, we've got an iron core with a part of it with a coil of wire, and on the other side another coil of wire. The relationship between these coils of wire, if that primary voltage is 110 volts and there's twice as many wires on this side, it will produce 220. So that's called a step up. It increases the voltage from one side to the other. The bottom one does it the other way around. We put a higher voltage in because there's less windings on that side. If there's 100 there and 50 there, it's a step down with a 2-to-1 ratio, which will give you 110 volts. So step up or step down. These are vitally important pieces of kit that they're everywhere. They're absolutely everywhere. Did you charge your phones this morning? You used one. You used one. They're everywhere. I've got 2 here. I'm running the laptop off one, the camera off one. Got transformers daily. Used daily. Laptop, phone, microwave, television, charge your car. You know what, these transformers, have you seen these transformers? Usually on poles in the countryside, because it's too expensive to bury the cables, the electrical cables, underground to distribute to maybe 1 farm or 2 farms or a small village. So they tend to, it's cheaper to put them on a pole. And there might be 5,000 volts going into that transformer, but it drops it down and splits it up and sends it to the village. More modern types of transformer or urban transformers, you see at the side of the road, usually with a railing around them and danger signs. And that's exactly what they're doing. You've got the high voltage coming from the overhead lines. They come into these little transformers from the substations. There might be 5,000 volts going in, and that reduces it down to usable levels of voltage that can be distributed to your homes. So again, another Faraday invention. So now we're going to just have a little video, it takes about 10 minutes, of the electric motor to just explain in a bit more detail how that works.
If you look around your house, you will see many devices that have electric motors, such as kids' toys, table fans, toothbrushes, hair dryers, and this electric cutting knife. But how does the electric motor work? You turn it on and somehow it starts rotating. Why is that? In this video, we'll cover the basics of electricity and magnets, and then put it all together to understand how the motor works. This video is sponsored by Brilliant. Let's start with something called a circuit. You have a battery, some wires, and a device that uses electricity such as a light bulb. Electricity flows through the circuit. But as soon as there is a break in the wire, the electricity stops flowing and the light bulb goes off. The path must be complete for the circuit to work. This is best done through the use of a switch. Electricity is flowing down the wire. This is called conventional flow. If we take the battery out and flip it, then the current will flow the other way. The light bulb will still work in either case, but there are some devices that will work differently depending on which way the current flows. Okay, so that's the basics of a circuit. Now let's come over here. This is a magnet. It has a north pole and a south pole, and it likes to attract other metal objects like these paper clips. If you bring another magnet towards it, opposite poles attract, and the same poles repel. Magnets don't have to be in this shape. For example, some magnets might be more flat like this. You can think of this magnet as always on. It's always working. You can't really turn it off. That's why it's sometimes called a permanent magnet. It's made up of many smaller magnetic domains that are lined up in the same direction. But later, I'll show you a type of magnet where this is not always the case. Let's take one of our permanent magnets and drill a hole in the center and put it on something that will allow it to spin. Now bring another magnet towards it. Our spinning magnet will immediately line up until opposite poles are right next to each other. Now switch out the side magnet. The same poles repel and opposite poles attract. If we keep switching out these side magnets, then our spinning magnet will just keep spinning. This concept of the spinning magnet is really important. We'll come back to it in a moment. Here's a metal bolt, which is not a magnet. It's made up of magnetic domains, but they are pointing in random directions. Now let's take a wire, wrap it around several times, and then create a circuit. The current through the wires forces the magnetic domains to line up. That means we've just made a magnet, or more specifically, an electromagnet. It can do the same things that a permanent magnet can. It can pick up pieces of metal, and it has a north and a south pole which will attract or repel other magnets. But the electromagnet is special in the sense that it can be turned on or off, just like the light bulb. You can't do that with a permanent magnet. Now watch what happens when we flip the battery. The electric current was flowing this way, but now it flows the other way. This will cause the poles on our magnet to switch places. North will become south, and south will become north. This is called reversing the polarity of an electromagnet. Instead of flipping the battery, an easier way to do this is to just switch the wires. You should be aware that the electromagnet will get very hot if it's on for a while. Just a caution in case this video inspires any science projects. Let's come back to our spinning magnet. This time we'll replace the spinning magnet with our electromagnet. As soon as we connect the wires, the magnet turns on and it lines up with the side magnet. Now in reality, connecting these wires would prevent the bolt from spinning freely. But what's important here is the concept of the spinning electromagnet. Now let's switch the wires to reverse the poles on the electromagnet. The same poles repel and opposite poles attract. Now reverse the polarity again. Same poles repel and opposite poles attract. If we keep switching the polarity, our electromagnet will just keep spinning. To make this stronger, let's bring in another permanent magnet on the side. Notice how this side has the south pole towards the center, and this side has the north pole towards the center. The side magnets work together to spin the one in the middle. This right here shows the very basics of an electric motor. But we need to make a few improvements. The two side magnets can be replaced with stronger curved magnets. And instead of a bolt with wires, we're going to use a metal loop. This is called the armature. Connect our wires and we have a circuit again. This time you can think of the electromagnet as flat like this with the south pole pointing up. Now the armature will spin until opposite poles are lined up. We can keep it spinning by switching the wires just like we did before. But this is a lot of work to sit here and manually switch these wires. We need to add something to the armature called a commutator. It's a ring with gaps on the opposite sides. The commutator will spin along with the armature. Now we connect the circuit with two brushes on the side. These brushes will slide along as the commutator spins, and they are spring-loaded so that they always maintain contact. the current flows from the wire through the brush, the commutator ring, the armature loop, and back through the other side. Now we have our electromagnet and the armature spins. As we come around this time, the brushes will switch contact to the other side of the commutator ring. Remember, there's two brushes, so this is happening on both sides. Before the switch, the current to the armature is flowing this way. After the brushes switch sides, current will flow the other way. This means the electromagnet switches polarity, which will cause the armature to keep spinning. This commutator ring does the same thing as switching the wires like we were doing before, but this time it does it all on its own. It will continue to spin as long as we're connected to a battery. Disconnect the battery, no more electromagnet, and the spinning stops. Now so far we've only used one loop on the armature. This will cause our motor to have an irregular speed, and in fact, we could get stuck in this position with the brushes halfway between commutator segments. What we can do is split the commutator ring and then add another loop. So first, the brushes are in contact with these two commutator segments, which turns on this electromagnet, which causes it to start spinning. Once we get to here, the brushes switch contact to the next pair of commutator segments, which means this loop turns off and the next loop turns on. Now this electromagnet wants to spin. The brushes switch contact and the next loop turns on. This keeps happening as our motor spins. It's almost like the loops will take turns being an electromagnet. Some electric motors will add many loops to the armature. This ensures that there will be a continuous spinning motion on the motor. This spinning force on the armature is called a torque. Stronger torque means a faster spin. There are some things we can do to improve the torque of the motor. Electromagnets are stronger when there are more wires. This is true when we wrap more wires around the metal bolt. And it's also true when each of our armature loops are made of many wires. The motor will have stronger electromagnets, which means it will spin faster. If you look at some pictures of real electric motors, you can see lots of wires wrapped around. And yes, this is the same reason. More wires wrapped around means stronger electromagnets. Another way to make this stronger is to use more electricity. Let's learn a few more terms here. The part that doesn't move is called the stator. In this case, it's the two permanent magnets on the side. These fit inside the edges of the motor case. The armature in the middle is also called a rotor. Remember, this is the part that spins. The axle goes through the middle here and then sticks out the back of the motor. What I've shown you in this video is called a DC motor. If you have a device that moves and is powered by a battery, there's a good chance there's a DC motor in it. Other types of electric motors will work a little differently than what I've shown here. No matter the type of motor, most of them will produce some type of spinning motion. Once it's spinning, we can use this to make different devices move. In this case, a kid's toy. Or even a fan that cools your room. The spinning of the motor can be converted to other types of movement, such as the side-to-side motion that we see in this fan. Or how about this electric cutting knife? Each blade is going back and forth. It all starts with the spinning of the motor to turn a gear, which then pushes these two pieces back and forth. So hopefully this video has made a few light bulbs go off in your brain. If you like learning new things, head on over to Brilliant. This is a problem-solving...
So, I hope you've learned a little bit from that. I've got an example of an electromagnet I put on the desk. So just have a go with that. And as it is at the moment, it's switched off, so it's not really doing anything. You connect the wire up to supply the voltage and create the electromagnetic induction. It picks up some paper clips. If you disconnect it, it drops them. That's an electromagnet. The motor that I've put on the desk here. You can see the commutator on the bottom with the split segments. About how the power goes to the different coils in it. And these are the little brushes that when they're spring loaded and they sit around that, they supply the power to the different segments, causing the motor to turn. Just as you've seen then on the video. I'll do that later. So now what I'd like to do is I'd ask you to all make an electric motor. So I've got some bits and pieces here, which I shall hand out. I've got some tools, some batteries. And a diagram, most importantly. And I'll explain this. There's a handout there for each of you.
Very much.
The first one is a picture of what it should look like when you finish. It's a very simple electric motor that if you follow the instructions, it will work. So let's have a look. I've got some tape, some pens to use as formers for making a coil of wire. What I'll do, I'll make one first. I'll make a coil of wire. Very simply, pull some wire off, hold a couple of inches to one side like that, and then wrap it around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then cut another couple of inches off there. That's your coil of wire. What you need to do with that is just wrap these round to keep it in place. Once or twice. Basically that's what you're making, just like a ring with 2 legs on. Who's going first? I'll cut you some wire.
Let the 3 do that, if that's alright, Mike, then I can
Yeah,
just-
that's sure.
That's alright, yeah.
That should be enough. There you go. It says if you need them. There's a picture of it on the screen now, so you can get an idea what it's supposed to look like. Right, all that.
Natural. He's missing a few coils line, but
The thing is with these, you need to be a little bit balanced. But we'll come to that. We'll see how it runs first. So once you've got your coil, how's it going? Ooh, it's a bit short on the legs, isn't it? Let's take it. A winding off. I didn't give you enough wire. That's one. One more through there. Okay, so when you've got your coils, we need to just get some with the sandpaper. On one of the legs you need to just remove the varnish with the emery board, emery paper, roughly where it's going to touch the clip, just the last inch or so. Just rub the varnish off, all on one side. Once it starts looking shiny copper colour, then you've got most of it off then.
Do it on the other side as well, yeah.
On the other side, you just do you hold it vertical, and just do one edge, one side, so it's half of it's taken off. You turn that so it's vertical. Put it on the paper so it kind of see like that.
Yeah.
And just take the top layer off the wire.
Don't destroy it.
Good. So we're getting there slowly. If you take one of the paper clips now and just roll them in that way, they form a natural eye in the middle. That worked. Looks like it. If you do both of those like that, and then take one to each end of the battery. If you use the big one, the big end. Put one on each side and just wrap the tape around. So it's here. Just like that, then just that's right, yeah. That's exactly what we need. That's it, slot it into the eyes. looking good. So just slot it in, support the ends into the little eyes. So we've almost got 3 electric motors. So I need a bit more tape on. Yeah, right, just go all the way around with it. Okay. So I won't let you have all the glory just yet. I'll wait till everybody's caught up.
Yeah. Sorry, I'm just reading along that.
So we're all at the same stage more or less. So all you need now, the final thing that's missing is a magnet. I'll give you a magnet. If you place that under the coil, if we've done it right, you might get it to work. Might need a bit of a boost start, bit of a little bit more balanced. Let's try it. Don't really want it to go then. Bit of fine tuning in. I think this one needs a little bit more. Just, without your notes. I'm not doing it on your notes. Anybody had any success yet?
No, I might need a bit more something.
Started on its own then.
Hey. Ooh. Soft.
Gosh. Oh, I forgot one going.
Juice power.
Forgot one going.
Oh,
What?
it's almost.
I'm determined to get this one going. It's so close. So you can get a bit of a feel to the experimentation that Faraday must have gone through to get his ideas, or to prove his ideas.
There's been a lot of trial and error, like.
Yay!
2.
Oh, it's going like this. It's going like that.
It's a high power on that one. Just put a bit more tape on this. Must have got all the variables absolutely right.
Just obviously trying dancing. That's glitching.
Welcome there. Will work. That was just broken over completely.
To give up.
It's given up by, yeah. Retired.
Might need a recharge. With the transformer.
What the heck is it?
Just dancing.
What's that?
Oh!
Mega power.
That's power, that.
Wow.
Can you power with that? Nothing.
Slightly out of balance if you don't hold it. It
Right, yeah.
shakes itself loose.
Oh, throw it down.
So today a bit of fun, but 200 years ago, that was so important, so important. So, what have we learned today? We can explain what electromagnetic induction is, know when and by whom this discovery was made. We've learned how the discovery led to inventions of numerous other electrical devices and have an understanding how an electrical motor works. We understand what electrical transformers do and what they're used for, and we've had hands-on experience of building a working electric motor. All 3 worked. Amazing, amazing, superb. So, it's very difficult to imagine a world today without the benefits, without these benefits that these and many other talented, curious people who dedicated a major part of their lives and were ridiculed in a lot of areas for their thoughts and experiments. But they paved the way for countless more inventions that are now part of our everyday life. And we haven't finished. It's still rolling on. But it's based on these fantastic discoveries. Thank you very much.
Thank you.
Thank you.
Thank you very much.
Good clap. Little round of applause.
A little bit early. Oh, sorry. Of course. Has anybody any questions? I'll try to answer them.
Right.
Is electromagnetic induction? Is it the same as like when someone says, oh, because I've got an induction hob at home, is that the same kind of thing or is that different?
Because it's an element that induces, you're not actually touching it, it's induced into the pan.
Right.
So it is induction.
Yeah. Right, okay. I've always just wondered how it works. I just wondered if it's the same thing.
So, do we know who invented electromagnetic induction? Faraday.
Yes.
And when?
1830?
1831. 1831. And there were other people involved, a lot of other people involved, but he has the recognition as being the father of electricity. Good, thank you.
Thank you very much, Mike.
Thank you.
That was excellent. We've really